morning, General Chemistry. So I'm going to take you through your notes using this video format. So you may have seen that you're on Edpuzzle, and how that's going to work is you won't be able to skip or run forward. You can pause though, so if you need to pause, write something down, then you can press play again. There'll be a couple questions embedded in this video. They're not for a grade, but you do have to complete them, so you just get a completion grade for doing the notes. And I can see if you finished the video or not, so please take the time to listen and watch the entire video as you take notes. All right, so we're talking about atoms in the mole. We did that intro activity where you got introduced to protons, neutrons, electrons, and the basic structure of atoms. So we're going to first talk about the history of atoms. To start, the atom is the smallest particle of an element that still retains that element's properties. So it's really the smallest unit of matter that under normal circumstances. The first guy we usually talk about when it comes to the history of an atom is Democritus. He was the first, way back in the 4th century BC, to suggest the idea of atoms, that everything could be broken down into tiny particles. And then John Dalton was the first person to be given credit for the atomic theory. All right, so we're going to talk about a few postulates of the atomic theory. So first one, he said that all atoms are composed of indivisible particles called atoms. Now I have false here, so I wonder if anyone can figure out why that's false. So the word here that is false is indivisible, which means that they can be divided. So can elements be divided? We now know that yes, they can be divided. So they can be divided into protons, neutrons, and electrons, and then even further from that. So this first postulate was incorrect. Next, he said that atoms of the same elements are chemically alike. Atoms of different elements are chemically different, which seems kind of duh, but back then there really wasn't a distinction, a way of distinguishing between atoms and molecules, and this was around the time where they were just getting away from Aristotle's 4-element theory, which said that everything was made of fire, water, earth, air. Okay, so it's kind of a big deal. It's chemically different. Those atoms are different from each other. Atoms of different elements combined in simple whole number ratios. So this basically means we can't have half an atom. All right, so when we think of something like water, which is H2O, oh, bad writing, H2O, this is 2 hydrogen to every 1 oxygen. Say it's a simple whole number ratio. We can't have half an atom. Okay, so if we break up half an atom, so let's take helium for example. Helium has 2 protons in the nucleus, usually 2 neutrons, and then it has, this is my atom, those are my orbitals. It usually has 2 electrons out in the outer ring. Now if we split that atom apart, what we end up with is just simply 2 new hydrogen atoms. So we can't have half an atom. Atoms are not subdivided in chemical reactions. So whatever goes into the reaction has to then come back out of the reaction. So when things react, we don't break the atoms. They just rearrange, right? They form new bonds and rearrange. If we do break the atom, that's called fission, and that's what we use in the atomic bombs, and that's what we use for nuclear power plants and so on. So in normal circumstances, under chemical reactions, we don't have a new element forming. We're going to take a quick look at this. I like to show this to students. Oh, I guess I may not be able to. Let's see. At first, we won't able to take a look at that size and scale. My link wasn't working, so we'll have to take a look at it another time here. Let's talk about the atomic structure. So we did go over this in that packet with the PhET simulator, but we'll quickly go through these. So we have protons. These are positively charged particles located in the nucleus. We abbreviate them P+, and the number of protons will tell you what type of atom it is. Neutrons are neutral, also in the nucleus, abbreviated N0. These tell us what kind of isotope is. They also affect the stability of an atom. Then we have electrons. These are our negatively charged subatomic particles located outside the nucleus in the electron cloud. We abbreviate these E negative, and they determine reactivity. So we're gonna be talking more about electrons as we get into chemical bonding. But really, protons and neutrons stay in the nucleus. Electrons, being in the outer shell, move around more. So here I just want to take have you take notice of the masses here. So protons and neutrons are about the same mass, but electrons are significantly smaller. So a lot of times we don't even take them into account when we talk about atomic mass, but they're pretty tiny. All right, again, feel free to pause. Basic structure, you probably know this. Nucleus, protons and neutrons in the nucleus, electrons in the outer shell. This is usually kind of what we think of when we think of an atom and its structure. Now, it turns out that atoms are a little bit more complex than just these nice circular rings around a nucleus, but we'll talk more about that as we get on. So a few vocabulary terms to add to your notes here. Atomic number, this tells us the number of protons in the nucleus. And it's the blue number on the periodic table in our classroom. So I'm going to add that here. Give me an ink color. I wonder if I can do it in blue. See, blue number on our AOUR periodic table. Okay, blue number. Now the mass number is different from the atomic mass. We actually won't find this number on our periodic table. That tells us the exact number of protons and neutrons in the nucleus of a specific atom. So these two are always going to be whole numbers. The next one, so to find the number of neutrons, we need to know the mass number. We can subtract the atomic number to get the neutrons, because our atomic number is protons, mass number is protons and neutrons. So if we subtract them, we can figure out the neutrons. Next thing we're going to talk about, so we've seen this kind of notation before in that PhET simulator packet, that atom builder packet. This number up here is the mass number. This number down here is the atomic number. So whenever you see it written like this, one on top is the mass number, one on the bottom is the protons. So this is what that atom would look like. Okay. If you wanted to figure out how many neutrons were in there, we know that we have 2 positive protons. Total mass number of 4, and that's here 1, 2, 3, 4. So we'd take 4 minus 2 would give us how many neutrons we had. So let's take a look at the isotopes. So we learned about isotopes in our packet already, but these are atoms of the same element, but they have different numbers of neutrons. So in other words, their mass numbers are different. So we're going to be doing more with that here when we get back. But atoms of the same element that have differing mass numbers. So take a look here. Neon has 3 forms: neon 20, neon 21, and neon 22. Notice the protons are all the same. The only thing that's different is their neutrons, so their mass is slightly different. So this number at the end, that's the mass number. 10 protons plus 10 neutrons gives us 20 for a mass number. There are 2 ways of writing isotopes. We see the hyphen notation, which is usually the symbol or the name with the mass number, or the nuclear symbol notation like this. So carbon with a 12, it's always accompanied by its mass number. Okay, so as long as you're familiar with that. Let's do a couple of these. Reminder, make sure you know how to do this. So how many neutrons are in each atom? So let's take here oxygen. This would be its protons, its atomic mass. So how many neutrons would there be? We'd have to take 16, minus the atomic number of protons, 8. So that means for this one we have 8 neutrons in oxygen. Here, 32 minus 16 means we'd have 16 neutrons here. And here for silver, we'd take 108 minus 47. Oops, sorry, pen. And we'd have 61 neutrons. Okay, if they don't tell you a charge, like all these don't show a charge, you can assume they're neutral. So if this one's neutral, there's no charge here, we can assume electrons would also be the same as the protons. So that's one thing you're going to see in the quiz that you're going to take after this and in the worksheet. So how to calculate average atomic mass. So atomic mass is an average mass of the atoms of an element. It reflects the different kinds of isotopes. And it also takes into account the abundance. So here's an example. 4 out of 5 atoms of boron are boron 11, and 1 out of 5 are boron 10. So it's saying if we have 5 atoms total, then 4 of those atoms will be boron 11, and then 5 of those atoms will be boron 10. So calculate the atomic mass of boron. So because 4 out of 5 would be boron 11, we take the AMUs, which is this mass number, that's the atomic mass unit, multiply by the fraction, multiply 10 by 1/5, because that's how many we have. So this would be our atomic mass for boron. So you can take a look, if you take a look at the periodic table, you'll see that the atomic mass of boron is about 10.8. So what this does is it allows us to say, okay, boron 11 is obviously the most abundant. That's why this number is closer to 11 than it is to boron 10. All right, and that's where we're going to stop for today. So on your worksheet, you're going to be seeing too this calculating atomic mass. It gives you an example of how to do it. We're looking for this number in AMUs. So now that you're done with your notes, you need to take the atomic structure quiz that's also on Schoology. Okay, you can use your notes, you can talk to people. You'll get 1 attempt. It's worth 10 points. So good luck, and let me know if you have any issues. All right, see you in class.